Hello viewers, welcome yet to another lesson on mathematics, and this is again for the upper basic level and specifically for grade 8, alright? Although other grades can also learn from it, okay? And today we are looking at similar triangles, okay? If you recall from our previous lesson, we have looked at what we call congruent triangles. Today we are going to look at similar triangles, okay? Now let's see what they are. Similar triangles are triangles that have the same shape but different sizes, okay? They have the same shape but their sizes are different. Now, when two triangles that are similar are being named, the letters are named in the correct order to show how they are similar, okay? So, naming of the triangles is important when it comes to similarity, okay? But the main take home from here is that two triangles that have the same shape but different sizes are what we call similar triangles. The same shape but different sizes. We call them similar triangles. Now you can see here, this example illustrates that. If you look at triangle XYZ and triangle PQR, if you look at them closely, they have the same shape, alright? But clearly, triangle PQR here is bigger than triangle XYZ. Looks bigger, alright? So they have the same shape, but their sizes differ. Okay, so therefore you can see that these two triangles are similar triangles, okay? And we can write that using this. We can say triangle XYZ with the symbol for similarity. That means triangle XYZ is similar to triangle PQR, okay? Same shape but different sizes. Similarity, okay? Now, the sides of similar triangles which are opposite to equal angles in each triangle are called the corresponding sides, okay? So the sides of similar triangles which are opposite to the equal angles in each triangle are what we call the corresponding angles. So you should get used to that so that in case in the future you have to start using corresponding sides, we should know what corresponding sides are, okay? These are the sides which are opposite to the equal angles in each triangle, okay? We call them the corresponding sides. Now, two triangles are similar if one or all of the following conditions are met. So now we are going to look at the conditions for similarity. Any one of them or all of them can prove similarity, okay? So let's see what they are. Now the first condition is all three sides of one triangle are proportional to the corresponding sides of the other. In other words, the ratio of the corresponding sides is a constant or is the same. Okay? Now if you observe here, we have two triangles here. The first triangle we have, the sides are 5, 7, and 11. And then the second triangle, the sides are 7.5, 10.5, and 16.5. Now, what this is saying is that if we take any two sides of one triangle as a ratio, and then you take the corresponding sides of the second triangle as a ratio, if we simplify those two ratios, they should be the same. They should give you the same. They should give you a constant, the same. All right. Now let's try and prove that here. Let's take this triangle. I take this side here as 5 over the other side. There is 7. 5 over 7 here. Okay. And then from the second triangle also, if I take the corresponding sides, you can see that this 5 that I took here corresponds to this 7.5 on the second triangle, okay? So if I take the 7.5, take the 7.5 over the corresponding side of 7, which happens to be 10.5. 10.5. Now, if I was to simplify these two ratios, they should be the same. Now observe, 5 over 7 is already in its lowest term. You can't simplify that, all right? But 7.5 over 10.5 can be further simplified. How? We know decimals. If I want to divide these two, I can easily get rid of the decimal by multiplying both the numerator and the denominator by 10. And if I do that here, this 7.5 will become 75, okay, over. And this 10.5 will become 105. Yes, 105. Now, if you were to simplify that, 75 and 105, you see that there's a number that can divide the both of them, okay? If we use 5, for instance, 5 can go into 7. How many times is that? That will be only once. Let me write this here. There will be a remainder of 2. And then you have 25. 5 into 25 would be 5 times. So you get 15 out there. 15 over. If you come down also divide, 5 into 10 would be exactly 2 times with no remainder. And then 5 can go into 5 also exactly once. Okay? So, still 15 over 21 can be further simplified using 3. And if we do that, 3 can go into 15 exactly 5 times. 5 over 3 can go into 21 7 times. So what do you observe? 5 over 7, 5 over 7. So the ratios are the same, right? So that proves that these two triangles are similar, all right? So that is this property, that the ratio of the corresponding side of, that all the 3 sides of one triangle are proportional to the corresponding sides of the other. So you can just take any 2 sides of one triangle and the corresponding 2 sides of the second triangle. If their ratios are the same, then you can conclude that those 2 triangles are similar. So this proves similarity. Okay? That's one condition for similarity. Now the second one is the corresponding angles in the 2 triangles are equal. Now that's an easy property, all right? If all the corresponding angles of the 2 triangles are equal, then we can also say that those 2 triangles are similar. You can see clearly here, comparing these 2 triangles here, but you observe that this angle here is 47, and the corresponding angle on the second triangle is 47. So those 2 angles are equal. Also, this angle right here is 28, and if you go to the second triangle, this angle right here is also 28. So again equal. Then you check the third angle, 105 degrees, and if you go to the second triangle, the third angle there also is 105 degrees. So all the corresponding angles are equal. So therefore, these 2 triangles are also similar. Okay, this also proves similarity. Okay, and then we have a third property. It says here, 2 pairs of corresponding sides are in the same ratio, and the angles between these sides are equal. Okay, that 2 pairs of corresponding sides are in the same ratio, and the angles between them are equal. Now, let's compare these 2 triangles here. This side here is 6 centimeters, this is 10, all right? And the angle between those 2 sides is 100 degrees. Then the second triangle, this side here is 9 centimeters, the second side here is 15. And again, the angle between those 2 sides is 100 degrees. So the angles between them are the same. But how about the ratio of the sides? if you took 6 over 10, 6 over 10, and if you simplify that, would that be equal to, the other triangle, which is 9 over 15? If we simplify these two, would they be equal? Let's try and see. 6 and 10 can be divided through by 2. And 2 can go into 6 exactly 3 times. 3. That should be 3 over. 2 can go into 10 5 times. So you get 3 over 5 when you simplify the first triangle's sides. And then the second one, where you have 9 over, you get 9 over 15. A common factor there could be 3. And if we divide them by 3, 3 can go into 9 exactly 3 times, over. 3 can go into 15 also 5 times. So what do you observe? The ratios are the same. 3 over 5, 3 over 5. And then the angle between them are also equal. So again, this proves that these two triangles are similar. Okay, this also proves similarity. Then, now, let's see if we can find a way to identify similar triangles, and let's see which sides can we correspond to, or which sides can we use as ratio. Now let's observe this. We have this line, let's name this line as, let's say, AB. I want to name it as, no, I already have AB here, so let me name it as XY, X, and then Y. All right? And then the other triangle, I can name it as, say, P and Q. Yes, PQ. Let's here be Q. Right. And if you observe here, is that line XY is actually parallel to line PQ, because you can see the arrows, all right? So these two lines are definitely parallel. So let's do some analysis here. Let's look at the angles and the triangles. Because these two parallel lines, we have two transversals cutting through them, all right? And those two transversal, they meet right here at F, okay? So now, if you just recall from our angle knowledge, you will know that this angle right here, this angle here, you can see that is angle AFB, that angle there, and this other angle right here, yes, I want to use the same color. So those two angles there, what do you observe? They are vertically opposite angles, which means they are equal. Okay? So at least we know that one of their corresponding angles are equal. But again, let's try to see this angle here. I'm making this as a green angle. Okay, that green angle here, that is angle GEF. Which angle can we equate it to? Looking at this diagram very carefully, this and this angle B here, observe what are they? This angle inside, but they are not on the same side, which means they are what we call alternate angles, all right? So, and we know that alternate angles are equal. So obviously this angle has to be equal to this angle. And because we know in every triangle, if you add two of the angles, you must get 180. If two of the angles are equal, then definitely the third angles are also equal. Because for both of them, the sum is 180. So if the two are equal, then the remaining ones are also equal. So you can say that this angle here, let's try to choose a different color. So we have seen that, of course, if these two angles are already equal, and we know that the sum of angles in any triangle is 180. So if the two angles are equal, obviously the third angle should be equal. All right? So therefore, whatever is here, this angle right here, that's angle EGE, that should be, that's this angle here in black, should be equal to this angle FAB. That's this angle right here. Right. See? So what we observe now is that all the three angles of one triangle here are equal to all the corresponding three angles of the second triangle. So these two triangles are definitely similar triangles. So if I was to do some ratio here, for example, if I wanted to get their ratios, to compare the ratios of these two triangles, I could take, for example, the red angle on this first triangle on top here, this triangle, the red angle. The side opposite that red angle is EG. Okay? Now, so if I take that EG, EG over, let me take another side of that same triangle. Let's say the side opposite the green angle, and that is FG. FG. Okay? Now I can compare this to the corresponding sides of the second triangle. Now if you go to the second triangle, the side opposite the red angle there is side AB. And mind you that you must be consistent with the angles, alright? I use the side opposite the red angle in the first triangle here, then therefore I must also use the side opposite the red angle in the second triangle. So that's AB. AB over. Now for FG, I took the side opposite the green angle here of this triangle. So therefore also I must take the side opposite the green angle of the second triangle, and that is AF. So that gives you the ratio, AF. So this works. And you could take any two sides you wanted, so long as you are consistent with the angles and the sides, all right? So if I take the side opposite green of the first triangle and the side opposite black, for example, of the same first triangle, there also, when I go to the second triangle, I must take the side opposite the green over the side opposite the black. You need to be consistent there. You cannot swap the sides, okay? And this could have been very useful in if some of the sides we are given and you are asked to find a missing side, this could help, okay? But the diagram can also be in a different form. You may have a diagram in this form. But observe here, if you look closely, you will see that there are actually two triangles here, all right? One inside the other one. The bigger triangle here is triangle ACE. You can see that, all right? And then the smaller triangle is triangle ABD. Now we need to analyze and see if those two triangles are similar. Now how do we do that? First, let's look at angle. And by the way, this BD is parallel to CE, okay? That's this condition there. So if we look at angle A here, it is common to both triangles, all right? They share this angle here. So all of them have this angle as A. Triangle ACE and triangle ABD, they all share the same angle. So they have one equal angle already. Now let's see if we can still find more equal angles. Now, this line being parallel to this line, so if we take this angle right here, that should be green. Okay, let's take it black, no problem. So if we take this angle there at B, that is angle ABD, and also we take this other angle here as C, angle C right here, no. Okay, angle C, what do you observe? These two lines are parallel. This angle is inside. This other angle is also outside. No, this angle is outside rather, and this other angle is inside. But they are on the same side. Now, these are what we call corresponding angles. And we know that corresponding angles are equal, which means whatever is here is equal to whatever is also here. So these two angles are also equal. So what we have here is already they have this angle in common, and then these two angles are also equal. But we know that they are both triangles, and every triangle, no matter how big or small they are, if you add the three angles inside of them, you get 180. So if two of their angles are equal, then obviously two of the sides are also equal. No, the remaining angles are equal rather. If two angles are equal, then the remaining angle must be equal, because for both of them, the sum is 180. So whatever is here is also going to be here. So what do we see in the end? All the three angles of one triangle are equal to all the corresponding three angles of the second triangle. So obviously, these two triangles, that's triangle ACE and triangle ABD, are similar because all their corresponding angles are equal. Okay? So we could have quite a bit of ratios here. If I wanted, if I take the triangle ABD, the smaller one, and I take angle, the green angle there, that's angle ABD. Now which side is opposite angle ABD, the green side, or the green angle? You can see it is side AB, all right? So if I take that AB over, I take any other side of the same triangle, let's say the side opposite the red angle, that is BD. Now I want to compare that. I want to compare that to any other two sides of the bigger triangle. And let's see. For AB here, AB was the side opposite the green angle of the smaller triangle. Now if you go to the green angle of the bigger triangle, that's triangle ACE, the side opposite the green angle of that one is AC. So I could say equals to AC here, AC over. Now BD was the side opposite my red angle of the smaller triangle. So therefore the side opposite that same red angle of the bigger triangle is CE. So this is over CE. That's one possible ratio. Of course there are many more, because I could have easily used any other size, any other two sizes I want, so long as I'm consistent with the angles, all right? So I could have taken the AD of the small triangle, that is AD, and AD is the side opposite the black angle, or the angle used with the black arc, that is AD. Over, let me take another side of the same small triangle. Let's say I've taken AD, I want to take AB, okay? That is the side opposite the green, AB. AB. And I want to choose other sides of the bigger triangle. What do I have here is AD was opposite the black here of the small triangle. So if you go to the corresponding angle for the bigger triangle, that will give you AE. Okay? So that will be equal to AE. AE here. AE over. Now AB of the smaller triangle right here was the side opposite the green. And for the bigger triangle, opposite green is AC. So this will be AC. So all these are ratios I can get from this one diagram. All right? And this, we can see that can be very useful when it comes to our next example, where we are required to find the length of some missing sides, okay? But this careful analysis is helpful, okay? Now, let's put this into use. Let's look at an example here. We have a triangle which is very similar to what we are just explaining, but now we have some sides given and some sides are missing. This is triangle PQR, all right, where we are told that PQ is 8 centimeters. We can see that from P to Q is 8 centimeters. And then QR here is 10 centimeters. And then PR is right here, is giving us 9 centimeters. By the way, here should be S, and here should be T. Yes, ST. There you go, all right? Now, S is a point on PQ. You can see on PQ, you have point S there, okay? And then, such that PS is 3 centimeters. So we know that PS is 3 centimeters. You can see it here, from P to S is what? 3 centimeters, it's given. Then, going back, the line through S is parallel to QR and meet at T. So, this ST is parallel to QR and it meets this PR at T. So, actually this here should be parallel to this. Those lines are parallel. Now, we are asked to calculate ST and also calculate TR. But we need analysis. First, this small triangle and this bigger triangle, are they similar? Now, from our previous analysis, we have proven that these are actually similar. How did we do that? We knew that first, they had this angle here in common, both triangles. Also, we saw that this angle here should be different color. That angle here was equal to this angle here because they were corresponding. We also saw that this angle right here should be equal to this angle right here, because if the two angles are equal, then the third must be equal as well, because they sum to 180. That should be red. I need a red color there. So okay, red. So that was our analysis there. So they have this angle in common. This angle is equal to this angle, and this angle is equal to this angle. So we knew that they are definitely similar. So we can use that now. What are we asked to find? We are asked to find ST. Now ST here belongs to the smaller triangle. ST is not known, all right? But on the same smaller triangle, PS is known as 3 centimeters. So if you take those two sides as a ratio, that side PS, okay, let me take this color back to red, is useful. So I'm trying to say here, if you take the PS and the ST as a ratio, that will say PS over ST. If you write that, PS over ST, and we equate that to, now let's look at the big triangle and see which sides correspond to these two sides of the smaller triangle. Now PS and ST, PS was the side opposite the red angle here, and for the bigger one, the side opposite that same red is PQ. Okay, so you're going to use PQ, And then ST was the side opposite the green, which is for the bigger triangle, is QR. So you're going to have, therefore, PQ over QR. So we have that PQ over QR. Right. Now let's put the numbers in. Okay. Do we know PS? Yes, we do. PS is 3. So I'm going to fix 3 there on the PS over ST is what we are looking for. So we don't know ST definitely. ST is not known. That equal to PQ. Do we know PQ? PQ, yes, it is 8 centimeters. So you can fix 8 centimeters on the PQ. So this will be 8. 8 rather, over. Do we know QT? Going back, no, QR rather. QR is 10 centimeters. So we know QR is 10. By the way, this is R. So this is QR, which is 10. And from here now, we can just do our cross multiplying. And if you do this, you have 8 times ST. That should give us 8 ST. Okay? 8 ST equal to, equate that to, if you multiply 3 by 10, that should give us 30. And then to find ST, we can easily undo the 8 by dividing both sides by 8. And that will give us over 8 here. Over 8. Over 8. 8 cancels out 8. And then you have your ST. Your ST being equal to, see what happens. 8 can go into itself once. 8 can go into 30. That would be 3 times. If it goes there 3 times, that is 24. That will be a remainder of 6. But we know 8 cannot go into 6, so we can add 0 to the 6 and put down a point here. Put down a point here. Then 8 can go into 60, that will be 7 times. Yeah? And that is 56, so there will still be a remainder of 4. There will still be a remainder of 4. You can still add a 0 to the 4, because 8 cannot go into 4. So that becomes 40. And then if you divide 8 into 40, you get 5. Okay. So, therefore, ST becomes 3.75. That's the length of ST. And we can do the same kind of analysis to try to find TR. If you go back to our diagram and see what we can do to find TR. Okay, because now we have done this already. And that's the solution for ST. Now let's go back to TR. TR is right here. Okay? But we know where TR is. We have PQ on that side, and the whole of PQ is 9 centimeters. Okay? So if the whole of PQ is 9 centimeters, if we can find one, because STR is one part of that 9, so if we can find the other part, that's from P to T, then we can easily subtract it from 9 and get our TR. So let's find a way to find the PT. Again, let's just do quick analysis here. I want to take PT of the small triangle over PS of the same small triangle. Okay? I want to write it here. So you can easily see PT PT over PS of the small triangle. I want to equate it to the corresponding sides of the bigger triangle. And PT was the opposite, the black here, and for the bigger one, that is the PR. Okay, and then the PS is right here, opposite the red, which for the bigger one is PQ. So over PQ. Over PQ. Okay, now let's fix the numbers in. PT is not known, so you can still keep writing PT because we don't know the length of PT yet. PT over PS is 3, so you can put 3 here. On the PS is 3. That equals to PR, that is this length here, which is 9. So you get 9 there, over, and then the PQ rather, PQ is 8 centimeters. So you can put 8 here, okay? If we now put 8 here, we can simply cross multiply this and see what happens. Cross multiplying this will give you PT times 8 or 8 times PT, which gives you 8 PT. 8 PT, that should be equal to 3 times 9, which should be like 27. Okay, now if we divide through here by 8 over 8, let me take this thing out, okay. Divide by 8, and also divide here by 8. What we end up having is 8 cancelling out 8, okay? So we have PT, which I will write here. PT would therefore be equal to, let's divide 27 by 8. 8 can go into 8 once. 8 can go into 27. That will be 3 times. That will be 3 times. But that will be a remainder because 3 times 8 is 24. So that will be a remainder of 3. But we know 8 cannot go into 3, so we can add 0 to that. And then put down a point here. Now 8 can go into 30. That will be how many times? That will be 3 times. That will be 3 times. Again, that is 24, so there is still a remainder of 6. Again, if you add 0 to the 6, because 8 cannot go into 6 without 8 cannot go into 6 rather. Now, but 8 can go into 60 rather, that is 7 times. If it goes there 7 times, which is 56, there is still a remainder of 4. Still now 8 cannot go into 4, so we add 0 again, get 40. But now 8 can go into 40 exactly 5 times. So that is 5. So actually our PT is 3.75. But remember, what we are actually looking for is TR, okay? But now that we know the whole length of P, we know PR is already 9, and now we know one part of that 9 is 3.375. So you can easily find the remaining part, that is TR, by just subtracting 3.375 from 9. If we do that now, you can now say TR would now be 9 minus 3.375. 3.375. So by careful subtraction, we can do it here and say, okay, this is 9.000 for easy subtraction. And then subtract 3.375, and then just subtract this. Quickly, this we know you cannot take 5 from 0, so we borrow from this 9, and that becomes 8. Yeah, get here, you borrow, becomes 9. Yeah, get here, that's also 9, and you bring it here, finally, and get your 10. 10 minus 5 would be 5. That is actually 5. 9 minus 7 should give us 2. And then 9 minus 3 also should give us 6. That should be 6. And then bring down our point. And then we have here 8 minus 3, and that gives us something like 5. So you get 5.625, and that is the length of TR. Okay. Now, with that, we come to the end of today's lesson. Till we meet again, goodbye.